get going here. So, welcome everyone to our session on innovations in fixed structure engineering. My name is Julian Fraze. I'm one of the program managers at NOWRDC. Happy to be here today with you all and with our panelists. In this session, as with the ones that occurred yesterday, we'll hear from our presenters and then we'll open the discussion up to Q&A for the last portion of the session. And then I'm just going to kick off here with a brief overview on where we're at with the fixed structure engineering in the world and in the US. So to date, offshore wind support structures have mostly been dependent on monopiles. Fixed offshore wind support structures have mostly been dependent on monopiles, which make about 75% of all offshore wind foundations currently deployed. Diversity in the types of economical substructures that are available is needed to avoid, for example, the import of thick, high-carbon steel plates, the construction noise associated with installing monopiles, the bottlenecks due to shortages of U.S.-flagged installation vessels, and the lack of competition that could raise costs. To lower costs, we need a number of solutions that encourage new and existing U.S. businesses to engage in the offshore wind supply chains. The speakers on this panel are going to present their work with NOWRDC projects that are investigating improvements or innovative approaches to fixed structure foundations or related supporting technology. Speakers and projects include José Cerna, the Chief Technology Officer at Esteyco, presenting on their project Self-Installing Concrete Gravity-Based Substructure, or the ELISA Technology. Charles Albany, professor at Texas A&M University, with their project, Vibratory Installed Bucket Foundations for Fixed Foundation Offshore Wind Towers. Paul Fleming, principal investigator for offshore wind control systems at NREL, presenting on wind farm control and layout optimization for offshore wind farms. And then we have a substitution for Eric Smith. I'm not sure if it's reflected here, but we have Eric Sells, the senior engineer and PI at Keystone Power Systems, presenting on their project, tapered spiral welding for U.S. offshore wind towers. And then we have also a substitution. We have Eric reflected properly. Eric Terhorst, R&D manager at Deme Group, presenting on their project, the TSP Foundation concept. So a couple of housekeeping items before we get going. We have a 2-hour session today. Initially, we had 6 presenters, but we have 5, so we have really up to about 20 minutes for each one of you to present. No intention to cut you off, so just please track your time yourselves, and I'll also sort of wave to you at a couple minutes. And then, we're hoping to open up for questions with the last approximately 30 minutes of the session. So all those questions, as with yesterday, will be submitted through the Slido app in order for me to give equal attention to those virtually attending. And then one final note I would ask, just if you could, or if it's not already in your presentation, let us know where you're at with your NOWRDC project. What stage in the project you're at, if you kicked off, and how are things progressing, sort of in your introduction would be great, so to frame the discussion. Great. And with that, the first presentation is José Cerna. Thanks.
Great, thanks a lot, Julian, for your kind presentation, and everyone for attending. And of course, thanks to NOWRDC for inviting us to letting you know the work we are doing, and of course we are very grateful for their support. So I will be speaking about the self-installing gravity-based concept we have been working on for several years. It's already operating in Spain with a pilot unit. We call it ELISA Technology. And yes, we're working on this project together with NREL and supported by NOWRDC to analyze how the structure the system could be implemented and scaled up for a potential US application. So I will let you know about the project. Right now we're in the mid. It's a 2-year project, so we are in around we surpassed the equator of the project. But I'll give you some details. So it's ongoing, but we have already done quite nice progress, which I hope to let you know about. So today I will arrange my presentation in the 3 main blocks. First, I'll give you an introduction of the technology itself, and then we'll give you a brief presentation on the project, and then go through the main milestones that we have already achieved and the main results we have generated. So starting with the ELISA technology, the ELISA technology, it's actually quite simple in concept, but yeah, quite demanding some of the systems we had to develop to make it real. And it's really well an innovation in the fact that it's at least up to now the only bottom fixed solution that can allow for the full installation of substructures and wind turbines, actually with no need for wind installation vessels, the big jackups that are conventionally used to install turbines, and typically monopiles or other foundation systems. In this case, it's the only system that can overcome this dependence, which can be quite a bottleneck, as we all know. And this is based on a gravity base that can actually temporarily act as a floating foundation with a base and a shaft. And we complement this with what we call the team platform. That is, a team is a transport and installation module, which can couple to this structure, and we can just tow it to the sea. So the installation is only based on tugboats, and then ballast it in a controlled manner to the seabed. Okay. The system may optionally also incorporate, a telescopic tower system. A telescopic tower would actually makes it easy for the onshore installation of the turbine. This is also, let's say, a novel system for bottom fixed solutions, because it allows for installing the turbine on harbor, which we see as a big advantage for industrialization and control working conditions. Now, this is the common way to go with floating solutions that we'll talk about this afternoon. But for bottom fixed, it's a novelty. With the telescopic tower, we can reduce the height of installation of the turbine. But depending on the project, this is only an option. Depending on the availability of cranes, it may not be needed, as I will describe. Okay. So the solution is open for a wide range of water depth solutions. I'll let you know which ones we are working on the U.S. East Coast scenarios. Okay. If any one of you is curious, we have a limited time, so I'm not putting it, but there's a video of the installation of the pilot unit in the Canaries in Spain. You can check it in the YouTube, and you will see with more detail some of the aspects I will describe now fast. Actually, and just as a clarification, the ELISA technology, as we call it, has different configurations that can be used depending on the circumstances of the project. It can be installed. It can use the conventional steel towers. So we have the base, we have the concrete shaft with this semi-submerged, and then we can use a conventional steel tower. Of course, this will make the turbine higher during installation, but as long as we have the right large capacity ringer cranes, this can work. Or the team platform that we use for installation needs to grow, but not very much, slightly. That's let's say the first option we are considering this project. It may also incorporate, as we did in our pilot, the telescopic system I talked to you about. This, for instance, we are working in an island, so we didn't have the large capacity cranes, and it was only one unit, so it didn't make a lot of sense to mobilize one large crane for only one unit. And we also wanted to approve and develop the telescopic tower system, which worked quite well. This we will also be exploring, but in a secondary, let's say, side activity in the project. And well, just for information, for your information, sorry, we also have what we call ELI, short for ELISA, which is also only using the foundation itself. Okay, so it's also quite cost-effective in terms of construction and self-installation. But this will not carry the turbine from the harbor, but just the foundation. The turbines can be installed with conventional with wind turbine installation vessels, jackups. This, for instance, we have worked in projects where they are doing part of the project with the monopile and part with the gravity base because of, for instance, ground conditions or boulders and so on. In that case, you're already mobilizing your installation vessel, so you can use the vessel both for the monopiles and the gravity base. Okay. And this slide just summarizes some of the advantages, which I think I already covered. So yeah, and I guess these slides can all be made available publicly later, so you can check that out. But I will just move, just to make sure I don't run out of time, to let you know about the project. But there's a lot of information and progress that I would very much like to let you about. So the project, I will let you know briefly about the team, who we are working on this, and what are the objectives that we're pursuing. So we are really happy and excited, and I can really say we are grateful and for a very fruitful collaboration we are engaging with NREL. So about ourselves, Esteyco is an independent engineering company. We work in all types of infrastructure, and energy is about half of our business, and we've been working in wind for more than 25 years now, for mostly in onshore, but for nearly 15 years now, working on offshore engineering and also offshore concepts. And Umbrella, I believe, needs no introduction. It's a really worldwide renowned institution for renewable energy and very good high capacities. A lot of knowledge on the wind turbine side of things. Of course, this is a solution it's the couple analysis, the joint analysis of foundation and turbine. So it's really great to collaborate with Umbrella in this project and to achieve together the results I'll let you know about. So there are a number of challenges that we'd like to address, but I just wanted to highlight some of them, probably the best. They are related. One, of course, is it's the critical dependence of installation vessels, and also the size, the continuously growing size of offshore wind turbines, which makes it critical for solutions to be scalable. And actually, these challenges are very much interrelated because, of course, the larger the turbine, the fewer the vessels that can install this. And in the case of the US, we have also the limitations linked to the Jones Act. So that's a bottleneck that is recognized, and that's a challenge that the technology can help to overcome, because it has good scalability and it does not require the installation vessels for installation. So the objectives we are actually pursuing with this project is first, the pilot we showed you was a 5 megawatt turbine. So we are analyzing how well can it scale for the next generation of 50 megawatt or even larger turbines. How can it be installed in the US, not only installed but also manufactured, how it can enhance the local supply chain, and of course, as any new technology, can it be cost effective, can it be competitive, because that's at the end of the day also the key factor that can help introducing new systems. And with that in mind, this is how the project is organized. We started a little bit over a year ago, and we will be finishing in 1 year. Like I said before, we're in the mid of the project. We did go through a go-no-go milestone with our NOWRDC and the DOE, which was a couple of months ago. And we're happy, of course, that we got a successful go decision, and they triggered some of the actual experimental and tank testing facilities we are right now carrying on. I will let you know about. Okay? We are also going through a number of quite interesting, I would say, advisory board meetings with quite a few major developers who are following the project and giving their insights and their recommendations, and pointing out the critical aspect that we should focus on, and that's been really helpful. 4 have already happened. And what you see on the screen is the main task that we have organized the project in. Of course, we have a project management, and then we first went through a screening of the. I didn't mention, but this project is focused on the East Coast, which it's of course for bottom fix it's where the development is happening and is expected. So we have a screening of the facilities and harbors where this could be implemented. Then we have tasks 2 and 3 working for the actual design from operating and for installation point of view, and we collaborated quite a lot with NREL in that process. And then task 4 is dealing how we can implement this, what are the scenarios and the strategies, and therefore what are the related costs for implementing this technology. Then we have some specific about the ballasting, and we have task 6, which is right now ongoing with the actual tank testing of the design we developed to make sure it performs as we expected and we predicted from the numerical and theoretical analysis and simulations. And we have then a number of tasks that will happen next year, working on the alternative with the telescopic, that tower that we mentioned, and also engaging in more detail with the local supply chain and analyzing different scenarios for application. I will let you know we started with a case in North Carolina, but we will also be analyzing other scenarios along the East Coast. So with that, let me please give you a summary of some of the key results that we achieved in each of these tasks. Task 1 I will skip quite fast. We did together with NREL quite a comprehensive screening and analysis of different harbor facilities, either existing, either planned, and then analyzing which could be suitable for for applying this, which would require some upgrades, and of course that's quite a few difference. Maybe some highlights. There are different construction strategies, either building on the dry with large yards or building on barges. Okay, this makes quite a big difference on the harbor. In the case that you want to build on land, a few of the harbors will require quite significant upgrading. There's a draft limitation which is quite common in the East Coast and less common in many of the European countries. But in our case, it's not a limiting factor typically, because our drafting harbor, it's around between 6 and 7.5 meters. So most harbors have this available draft. And what is a more common limitation, as we all know, is our air draft restrictions, particularly in some areas. If we are carrying the turbine, in our case, or with floating, we cannot go, of course, under bridges, and there are quite a few harbors, particularly in the northern part of the East Coast, where this is a limitation indeed for the applicability of this system. Moving on to the task dealing with the design. Here you see some details. I don't know if you see the actual design as after, of course, quite a few loops. We reached for the 15 megawatt IEA turbine by NREL and the DTU in Europe. This is a publicly available turbine, but of course in our case we had NREL on the team, so it was quite effective to analyze how it would perform. And we chose, let's say, a reference design with a 35-meter water depth. The technology can be applied. We have studied even in Massachusetts up to 65 meters, and some other projects even less than 20 meters. But we chose this as let's say, a representative water depth of an average condition in the East Coast, and we selected mid-ocean conditions applicable to New York. They can be a little bit harsher farther north. They can be more benign in the south, but New York was also chosen as a reference in agreement with NOWRDC. And what we got is a foundation base which has around 39 meter diameter. I should mention that we will also be analyzing different alternatives. This solution we can choose to ballast, to generate the weight we need only with water, which has some advantages in terms of operation, in terms of the commissioning, and but it does require bigger dimension and bigger weight of concrete. In this case, we have a little bit less than 9,000 tons of concrete. There are alternatives to use the solid ballast, sand typically, to gain weight. This can reduce the size and the weight, concrete weight of the foundation. This will also be analyzed in other scenarios, but we started with, let's say, the situation that generates the larger foundation size. And in tasks that are coming out, we will analyze also alternatives with solid ballast for comparison. Okay, this gives you a little bit more detail on the actual sizing of the foundation. We did carry out a lot of in ourselves, and this was really fruitful because we did our own load analysis and a couple load analyses, and NREL did their more detailed analysis with OpenFast, and we could compare, and then we learned together, and the alignment was quite good, and it was, I think, a very interesting and fruitful process. Okay, so what you see there is the shape of the shaft, which, as you see, is hexagonal instead of circular. It has to do with the coupling of the platform we use for installation. This allows for very robust coupling, and even though, of course, this system actually behaves as only one body in the water, then the forces need to be transmitted between the shaft and the auxiliary platform that can be reused, and this shape makes it possible to make it very robust, and that we don't need to invest material in the system that will not be used in the operating condition. This also allows for a quite simple geometry, so it's a constant geometry shaft, vertical walls base, and in terms of construction strategies and cost efficiencies, this is also helpful. Also, a thing that we're getting as compared to other typical, let's say, cone-shaped geometries is that because we have a slender shaft with a quite similar diameter, a little bit bigger, but quite similar diameter to a monopile, we're trying to gain transparency and reduce of course, the loads of the storm waves that we need to live with the hurricane-prone areas of the East Coast. We also did go into detailing of secondary steel elements, which are relevant for the cost analysis we performed. And with that design, we went together with NREL to analyze how this would work from an installation point of view in the conditions of the East Coast. We decided weather restrictions that could be, let's say, permissive enough to allow for a sufficient number of installation windows. So, as I said before, the installation is based on coupling the team platform to the shaft. This is providing high stability all along the installation process. Then we ballast the structure with a control ballasting process of the different cells, and then we can decouple the team platform and reuse it with different units. The towing speed is typically around 2.5 knots. It can go faster. For instance, if we have a long distance to tow, we can use larger tacks to reduce the duration of the weather windows. Well, this NREL developed a quite detailed analysis, and the results we got were good. One thing good thing we have is that we have a big mass on the top. This generates high periods, which are not affected by the wave periods, so we can this results in low excitation by the waves and low motions with reduced tilting, which is what we were looking for, and we want to make sure. And we checked that with NREL that the forces and the movements that the turbine is seeing are very comfortably within their design parameters. And finally, and I'll just I can go through all the I cannot go through all the details, as you can imagine, but the first exercise we did, we will be doing another two of implementation strategy in 3 locations that we selected along the East Coast. So first one is the one I will be showing, it's North Carolina. Then we're choosing another one in Virginia and another one in New York. Okay, in this case it was the Wilmington wind energy area that you may be familiar with, and we did an analysis of how the solution could be built and implemented. I just wanted to comment a few things in the few minutes I have left. It's a important thing. It's the construction strategy. So we're aiming to import, so to say, a solution that's been very effective in Europe, particularly in some countries, and also in Japan has been quite a lot used. In Spain we have used it a lot because we have deep waters on the harbor. So the mass production, serial production of large concrete caissons has worked very efficiently. It's a very cost-effective solution for producing a repetitive number of concrete units. We're talking that these elements, which are often twice as heavy as our foundations, are built one per week. It's simpler in many ways, but there are a lot of lessons that can be implemented. Most of all, they are built directly on floating barges, so they don't need a lot of area on the harbors. And this is of course a big advantage. They do need some wet storage, as I will explain. So this is just to give you an idea, and like I said, I cannot go through all the details. We did some theoretical exercises of how this could be implemented and the requirements we would need on harbor. When we build on barges, we need some certain quay length, nearly more than 500 meters, but we need very little area and very low bearing capacity. Sorry, I'll go quite fast because I'm running out of time. Just to let you know that based on these scenarios, I'm going through all the construction, local prices, installation strategies, workability, and a marine spread for offshore installation. We developed a quite comprehensive and detailed budget, which we worked together with NREL and they reviewed. And we based it in these 5 main chapters with port preparation, fabrication, the logistics, and the marine operations. And of course, I'm not going through all the details, but just to let you know that there's a quite detailed, and this, of course, the plan is to make it all public, so a very detailed analysis of the cost of each materials and the bill of quantities to analyze how the solution could compete with the monopiles. It's true that this first scenario is quite favorable because the labor cost in North Carolina is quite lower than other states farther north. But in this case in particular, we did reach quite positive conclusions with the solution being cheaper than the monopiles. And the savings in let's say substructure construction did compensate for the extra cost on seabed preparation, which may or may not be needed, but in our assumption on safe case it was needed. And just to end, sorry I took a little bit more time, just to let you know a little bit our status today. We did complete also, that was task number 4, we did complete task number 5 about how to industrialize and the ballasting system we use to ballast the structure. We're working on a let's say, kit that can be more plug and play for faster installation and construction strategies. And we are right now going through a tank testing campaigns, and we were trying to actually experimentally demonstrate and confirm that the conclusions we got from the numerical simulations you saw are consistent. This is a little bit delayed because we were quite ambitious in some of the elements we wanted to do. We wanted to test different ballasting and different water depths. And well, it's a little bit delayed, but it's ongoing, and hopefully next year, when the project is complete with this and other tasks, I'll be very happy if I can let you know about all of it when everything is complete. And with that, well, thanks a lot for your attention, and I'll be happy later to take any questions. Thanks.
Great, thanks. I'll turn it over to you, Charles.
All right.
Okay. Thank you. I'm Charles Albany from Texas A&M University. Our project is Vibratory installed bucket foundations for fixed foundation offshore wind towers. I don't mention here, but our project manager was Corey Grunfeld, and I would like to offer my thanks to her. The project team, I'm the PI. I'm from Texas A&M University. My specialty is offshore foundations and anchors. In this case, it's on the foundation side of things, fixed foundations. Professor M.H. Kim, also from A&M, he's specializing in ocean engineering. Our industry partner was Subsea 7, Seaway 7, 3 people in particular. Paul Hughes is the technology manager. Alan McClay is based in Scotland, and he has a wealth of experience on European experience and also in Scotland for fixed foundation installations. And then Zach Skelton is based in Providence, and he provided a lot of input on U.S. supply chain vessel limitation issues and port limitation issues. So that's the team. What we're looking at is bucket foundations for fixed towers and the use of vibratory installation to accomplish it. It goes a little bit beyond vibratory. The first several tasks were more the geotech side of things, develop a model for installation in sands and clays, size the bucket, a single bucket rather than a monopile or a tripod foundation. A bucket does have the capacity, it's relatively compact, so wet tow is possible, so you don't necessarily need barges to tow it to site, so that was viewed as a big potential benefit of this. As you'll see, it does offer advantages, but everything has a price, so there are some prices associated with the wet tow. And then the final 2 tasks were, for buckets, the big competitors are vibratory installation and suction installation. And we did a comparative evaluation. And then on the transport side of things, the wet tow method of transport was compared to the more or less existing method of barge transport for the buckets. Just for definitions, so everybody's on the same page, just defining the components. So the bucket or the caisson, interchangeable terms from our standpoint, and the column would be more or less fabricated together. And that's what we're looking at installing. The transition piece contains sensitive equipment. In a nutshell, for vibratory installation, we ruled out installing with the transition piece there. For suction, it is possible, and there is an advantage to that. Early in the project, we considered the possibility of fabricating everything onshore, or assembling everything onshore and then towing it out, so the turbine tower and the rotor. That fell by the wayside pretty quickly. So after our first IAB meeting, we more or less said, let's just focus on fabrication in port and then the transporting and installing of the bucket and the bucket and the column. Okay, so a bucket installation, so it's shown on the 2 competing ones we're looking at in this study are the, as I said earlier, the vibratory installation or the suction installation. And they wouldn't necessarily both be done, but it is possible, and maybe one of the better uses of vibratory, or certainly a large potential for vibratory, is that when suction does not work, to keep it as a backup. So Okay, so there they are. In this sketch, it shows the vibratory hammers being above the water. So, but they do, if there's a need to put the hammers on the side, they do have submersible hammers, underwater hammers that could be deployed. Okay, if you haven't seen a vibratory hammer for offshore use, that's shown in the lower right. As you can see, they're fairly massive. There's actually 3 hammers there. One beauty of vibratory hammer installation as opposed to impact hammers is you can use multiple hammers so long as you vibrate synchronously. So they've had projects where they've had up to 8 hammers being deployed at one time. So what you see is, well, it looks like a single monolithic unit, but there's actually 3 hammers there. Okay. The other aspect of it is when you tow out, depending on the operation, which I'll get into later, there's the heavy lift vessel. So in the upper right is a picture of a heavy lift vessel. And the new generation have fairly high crane capacity. I think that's 5,000 ton crane capacity there. Okay. For those that are not familiar with suction caisson, very brief intro to it. You lower your foundation to the seabed, and it's sealed on the top, and you have a valve, and you attach a pump to that valve. That valve generates upward flow. In sand, well, that valve generates an underpressure, so that pressure differential will force the caisson into the seabed. In the case of sands, you actually have 2 mechanisms. The upward flow actually liquefies the soil. It's like a quicksand. So that greatly reduces your penetration resistance. And so when you have that effect, it's a very relatively problem-free installation. Now, one catch for sands, if there's anything interrupting that flow, like a clay layer, that doesn't happen. And so you see on the slide, on the picture in the middle, I have the flow and the no-flow condition. So, and it's the required underpressure. So if you have the optimal condition of the upward flow, relatively low underpressures are required to install it. If that flow gets inhibited, installation's still possible, but you have much more resistance. And there are ways of overcoming that. They cycle and they could jet, but in general, if you have something like where it's stratified and you have that, the upward flow can't happen, life becomes more difficult. In clays, it's a matter of pure brute force. You apply the underpressure and it forces the caisson into the soil. It's usually not a problem because clays have lower, their undrained strength is relatively low compared to sands. So usually it's a relatively simple operation, especially in like soft, normally consolidated clays. Now, penetration in sand, this is for the vibratory. The way vibratory works for sands is when you vibrate, you generate pore pressures, which weaken the soil. When you weaken the soil, basically the bucket goes in under its own weight. So that's the way vibratory works. So, and it's a very rapid method of installation. So these large buckets you're looking at 15 minutes installation time to do that. By contrast, suction installation might be several hours. So it's a very rapid method, especially in sands. An early task in this project was to develop a model, and the intent was like a simplified spreadsheet-based, something to do a quick screening tool. So for a given bucket size and a given set of soil conditions, you could very rapidly determine what kind of hammer capacity you need. So that what you see encircled or enclosed in the red square there is like a simplified formula I came up with. It turns out the resonance happens, but it's not an issue. It happens at relatively low frequencies. It's not a big factor in the installation process. Penetration in clays, there's a lot of skepticism early in the project and in general in the industry on whether you could use vibratory installation for clays, because unlike sands, clays do not liquefy when you cyclically load them. However, you can just by brute force, with your hammer driving force, install it. So vibratory hammers are not optimal for clays, but they can work. So so if you have a clay, probably if you had, as you'll see later, if you have a clay deposit, you'd probably rule out vibratory. But if you have interbedded sands and clays, vibratory is still possible. So anyway, a whole task was devoted to comparing these. General conclusion was for uniform clean sand deposits, vibratory and suction work. So it's just 2 viable methods. There's a slight edge in one sense for vibratory in shallow water depths, since you're imposing a suction. If you have 0 pressure or negative pressures in water, the water boils, so that's cavitation. So there is a limitation in shallow water. So about 30 meters or less depth, you have a significant limitation on the suction side that you would not have for the vibratory. And then kind of a modest issue, a suction bucket requires a lid, so you can do the suction. Vibratory doesn't require it. So a little bit more steel required for a suction bucket. Uniform clay, I think, was hands down. Suction just works better. There's by its very nature, Vibratory is now well suited to just pure clay deposits. And I think where Vibratory has, I think, a lot of potential is when you have difficult interbedded deposits, where, as I said, when you have interbedded deposits and you don't get that upward flow that you need to make suction work well, Vibratory doesn't have that limitation. So, okay, I do make a point. There's when I get into discussions with people, some people say, well, we can make suction work in heterogeneous deposits. Heterogeneous is a big class of, it's like infinite varieties, but I think my sense is, and my conclusion is that a more robust, the Vibratory would be more robust solution in those heterogeneous deposits. As far as sizing, we had to size the bucket, so it's a big dominant concern. The driving force is the huge moment you have from a 15 megawatt wind turbine. So, and that kind of drives the analysis. What's shown there is for dense sands, about 16 meter by 16 meter is what you're looking, although you can vary the aspect ratio if there's some reason to do that, and it's shown there. In medium dense sands, you need a little larger bucket, say 18 meters, something like that. Okay, and then another issue is the wall thickness. Vibratory is less load demand than suction. Having said that, so in principle, you could maybe use thinner walls for Vibratory. However, they're already kind of pushing the envelope on wall thickness as it is right now. The diameter of the wall thickness ratio. My background in oil and gas was you wouldn't go above 140, 160. So you see that on the plot there. They're now in the North Sea doing these aspect ratios up to 209, so they're already pretty thin. So I more or less saw it as being a wash on with the wall thickness. The Vibratory, in principle, you can maybe try to push the envelope a little bit, but it's already getting a little scary. Anyway, and those were based on buckling analyses during the installation. That's a little sketch on that shown in the upper right. On the installation side of things, if it's a compact bucket, that introduces the possibility of floating it out. So Professor Kim devised a method where there's a wrap buoy and which to provide buoyancy. You wet tow to the site using 2 to 3 tugs, and then you install it, and then you lower to the seabed by detaching the buoy, the wrap buoys, and then you install by either Vibratory or suction. So a big benefit is you don't need barges, so you avoid the need for those Jones Act compliant barges because it's just tugs. And then you also don't need a heavy lift vessel. Well, if you're doing suction installation, you don't need a heavy lift vessel. So that another major asset that could be avoided with this approach. As you can see, you need a crane in port. So you need a port facility with a heavy lift crane to lower it into the water. Okay, barge transport. This, just a quick sketch of, kind of a condensed sketch of what it takes is, you have a barge, and then you don't really need a crane to lower that onto to move the units onto the barge, so you float it out. Once you get to the site, you need a heavy lift vessel to basically position that and then achieve the installation. So the potential liabilities for the barge transport method is you have to have Jones Act compliant barges, and you need a heavy lift vessel at the other end. In our last IAB meeting, they said this is all well and good, but what are the transit cycles? So in response to that, we took a quick look at, for 2 sites, we picked, talking to Zach, he picked 2, he picked just the New York Bight area was the target location, like a generic location in the New York Bight. 2 locations, port locations, Baltimore, Maryland, and Norfolk, Virginia. And then the tow distances are shown there, 390 nautical miles and 250. For transit speeds, for the barges and tugs, we assumed 6 knots. However, if you're towing, that's going to slow your tug down, so we use 3.3 knots on the way out, and then on the return leg, 4.5 knots. So then just did some quick transit calculations. It's not shown there, but the port just loading is actually not a trivial operation. It turns out that based on the experience in Europe, about 4 days of the operation to actually get the unit out of the harbor. So when you put it all together, depending on, also For barge transport in shallower water, for those large barges, say 400 foot, shallow water, 3 foundation units could be possible. As you get deeper, stability concerns start becoming more prominent, so 2 foundations per barge. So that was factored into the calculation. So based on that, and a 1-day installation time, actually it's a little less than that, about 18 hours based on experience in Europe, so I used 1 day. So anyway, there's the total cycle times. So for the barge, about 10 to 13, and wet tow similar, although for different reasons. But it's a little slower, but you only, the wet tow you can only transport 1 at a time. I think the big the big issue on not only just the cycle time, but how many barges it takes to keep up with the pace of 1 foundation per day. So about 3 to 6, and that actually matched with some of the numbers we were hearing from Europe on their installations for fixed foundations. For the wet tow, that's kind of the big, I said just the downside. You just need lots. You can only tow 1 at a time, and you just need lots of, to keep up a pace of 1 foundation per day, you just need lots of tugs to do it. And okay, the little transit cycle analysis you see in the figure, they assumed no downtime, but we recognize there is downtime, so the note at the bottom. When we were looking at the total installation, we made the assumption that the construction season would be 6 months. And you can encroach on that, I understand, and also uptime, we were, depending on the exact time of year, 25 to 55% uptime during the construction season. And from that, we concluded that, at least for the foundations, for a 1 gigawatt farm, which will be 67 foundation units in a single season, is possible. Okay, port facilities, I'm probably running out of time, so how am I? 5 minutes, okay, yeah. We looked at port facilities more from the perspective of the wet tow versus the barge operation. And there's a lot, it's come up in other talks too, and I also didn't mention a few minutes ago, but to make my schedules work, it assumed that you have a marshalling yard with enough units ready to go so that fabrication would not be the bottleneck. So that means you need lots of area to do that. Okay, so, but that really applies to both methods. But, and there's air draft, horizontal clearance, key length, key depth, et cetera. From the standpoint of the comparative analysis for the wet tow versus the barge, the big issue is you need a crane for the wet tow because you have to lower it into the water. The barge transport you wouldn't need then. And I think it's come up in several talks that we actually looked at, I think, 12 different sites. Really, there's no ports right now that could really totally support the operation. But okay, so the barge transport comparative study. Okay, the transport time's similar, up to 6 barges for max production. That's 1 foundation unit a day. You could do a little better in shallow water because you could transport 2 foundation units instead of 1. You do need a heavy lift vessel, so there's big, massive cranes, and then, well, you do not need a crane in port. Wet tow transport, similar transit times, so you need lots of tugs because you're only transporting 1 unit at a time. After I showed this to Professor Kim, he said, well, maybe you could get by with 2 tugs, so it might not be as bad as you see there, but people were, when I showed it to my team, I showed these numbers, they were kind of shaking their heads saying, I don't know where all these tugs would come from, but anyway, that's, like I said, you avoid the need for Jones Act barges, but you do need lots of tugs to make it work. A large crane required in port. You can avoid that crane. I talked to Professor Kim about that. There are like dry dock options where you could avoid having to have that large crane on the site. Wet tow transport, not well suited to vibratory. For a simple reason, vibratory requires a crane. And the whole advantage of wet tow is you don't need the heavy lift vessel, so it's kind of self-defeating to have wet tow when you need to, if you're going to use vibratory installation, because you need a crane out there at the site. Okay, and that's all I have.
Great, thank you. Yeah, moving on to you, Paul.
Okay, thanks very much. My name is Paul Fleming. I'm the principal investigator for wind energy control systems at NREL. And I'll be talking about our project, wind farm control and layout optimization for U.S. offshore wind farms. We're really in the last month or two, so I thought I'd use this presentation to try to put the overall project into some kind of perspective and ending. So some of the ending parts are a little bit preliminary, but we're pretty much there. Okay. So first, if you aren't familiar with wind farm controls, I thought I'd do a little bit about that. So a normal turbine controller, you have basically a couple of inputs, like you can measure the wind a little bit. You can look at the rotor speed. You use the blade pitch and torque and yaw to control the turbine to maximize energy production and keep the turbine safe. And your goals are to maximize your output and to minimize loads. In general, then, within a wind farm, every turbine sort of uses information it collects itself and controls itself for its own benefit. And so you might say, you know, if you look from the farm's perspective, this might be considered a type of greedy algorithm. In wind farm control, we look at different ways of cooperation. So either the turbines can share information, or maybe they consider objectives at a farm level where working together yields some sort of benefit. Within the kind of categories of wind farm control, wake steering is the one that I've spent the most time on. Let's see if this video will... okay. Well, anywho, in wake steering, the turbines use an intentional offset of their yaw alignment angle to induce the wake direction to shift away from downstream turbines. And even though you pay for that a little bit on the upstream turbine, you generate enough additional energy on the downstream turbine to make this net improvement. Here's another video you can't see. But in the early days of this, we did a lot of work with large eddy simulations to try to build up confidence that, you know, in various situations, you could actually, you know, kind of produce this yield by applying the correct offset angles in different conditions. We use these numerical studies to develop our Flores tool, which is an open source framework for the design and analysis of wind farm controls, but also layout. So, you know, the two things kind of go together. Layout can be used to diminish wake losses, and so can wake steering. And so we were building up this capability for thinking about what is the net benefit of wake steering for a given built farm or a farm yet to be built, you know, if you considered it in the layout phase. We started, you know, working on designing control. Sorry, one more video, then there's no more of these. The designing controllers into, you know, using the Flores tool, then testing them in the higher fidelity models like the LES codes. And in the last few years, really running these at different commercial farms to demonstrate that our, you know, our achieved results were in line with the predicted results from the model. So here, this is from a wind farm in Colorado where we ran a test using 3 or 4 turbines. We've done more testing recently at other farms. You know, the number of turbines involved is going up, but mostly onshore. Okay. So finally, now coming to this project, there's a lot of reasons to think that like technologies like wind farm control are especially well suited to offshore applications. This has to do with things like the large rotor sizes are to play to its benefit, the heights, the lack, I should say, of terrain complexity, the low expected turbulence, especially in U.S. conditions, the presence of atmospheric stability. All of this sort of means that we expect it to be most applicable to offshore, even though we've done most of the testing onshore so far. So that then brings us to the project. So in the project, we propose to first develop and validate computationally effective wind farm modeling and optimization tools for U.S. offshore conditions, and then apply them to a detailed cost-benefit analysis. So the idea here was, you know, take all of these models, make sure that they are, you know, looking well for offshore cases, and then look across U.S. Offshore expected development and try to show what the benefit of applying technologies like these would be. This was a three-group project. So myself, I'm from NREL. We also worked with Cornell University and Equinor. And the project was divided into 4 tasks. So the first task was about characterizing U.S. offshore conditions and trying to talk a little bit especially about how they might diverge from sort of the North Sea cases where a lot of the SCADA data we can get our hands comes from. In task 2, we would use those learnings as well as some SCADA data from offshore farm to develop a validated model of fluoris for offshore conditions. In task 3, do our optimizations over wind farm design and control. And then in task 4, come into some cost modeling and make some conclusions. So now I'd like to step through project outcomes across these tasks. This last month we wrapped up task 4, so I think, yeah, I can get into it. So in the beginning, the work was to identify where we wanted to do this analysis, and after some iteration with our advisory board, settled on 3 locations, the Vineyard Wind Site in the Atlantic, Humboldt in the Pacific, and Hawaii in, Hawaii. And if you went to Nikolai Bodini's talk yesterday, we were using some of their work as inputs to our work because they had done these large-scale wharf analyses. So these white boundaries are actually the wharf domains that we borrowed from them. We're also, what they mentioned too affected us as well, that while they had this capability for Vineyard Wind, there was no LiDARs for Humboldt when we started the project. So we were also a bit, and I'll talk about that too, stuck there. We also were able to get SCADA data sets from some offshore sites in Europe. So these are from Shell, Ørsted, and Equinor. They were able to contribute SCADA data to the project, which we could use to assess how our engineering model of wakes was doing that we would use in the later analysis. So starting with characterizing U.S. offshore conditions, there was other projects that were doing a more general atmospheric characterization. So we have a very particular angle on how does this affect our sort of analytic models of wakes and wake steering. And so we looked for things that were very clearly different between what we were seeing in Europe. So the European farms are in here, and the 3 U.S. farms are these 3. And this is a histogram of wind direction, just showing that something that really jumps out is 2 of the sites, Humboldt and Hawaii, feature highly directional flows. And if you think about it, this matters quite a bit for how you do the layout, because you don't have to think about every direction. Most directions are fairly uncommon outside of the dominant ones. And we could, when we did get LiDAR data for Humboldt, we were able to validate that it does indeed look quite directional. So this is going to be later in the later task fed into the analysis when we do AEP calculations and things like that. And really, I'm just kind of touching the highlights because this is sort of a shorter presentation. So a lot more we said in the full report, which we'll make a final report in the next few months. Another big batch of work came from comparing the performance of the fluoris engineering model to the SCADA data. So we did this in a series of 3 published papers. In the first one, we looked at fluoris's wake modeling against offshore SCADA data given to us by different project partners. And the figures on the right are showing basically the energy deficit of the turbine indicated in red over the course of directions relative to an unwaked turbine. And if you look around here at the 125 direction, the turbine is in the wake of a single turbine. And our existing model, shown in blue, is a pretty good match to SCADA. But as we roll up to the northwest, and the turbine is at the rear of a lot of other turbines, you can see our model at the time was under forecasting wake losses. Sometimes this is referred to as like a deep array effect, or sort of opening up on a cluster wake. So under forecasting the wake losses there, we worked with the other project. So we are one of the projects paired with an Innovate UK project. So Majid Bastanka of the University of Durham and his student, we produced a new model of the cumulative wake of wind turbines to try to assess the fact that, the sort of analytic sum squared combination of wakes is representative of small numbers of turbines, but not large number of turbines. So this was giving us a way to better account for the wake losses at the back of the farm. And then finally, in a third paper, we showed that this new model shown here is the red dashed line resolves this issue nicely. And so we feel much better about our ability to model large offshore farms at the end of task 2. Okay, then if we get into task 3, now we can take the model developed in task 2, the sites identified in task 1. Task 1 also gives us wind roses and site characteristics to feed into the model. And here, I think things shifted a little bit from our original plans. So we had this, NOWRDC had this great suggestion to put together an advisory board, a few really helpful members on the board coming from developers made some good suggestions. So we had originally thought, well, we'll just propose some sort of like academic boundary, like a square or a circle, and make some sort of a baseline layout and compare to that. And there was a much stronger preference for working with BOEM, grabbing some realistic boundaries and performing the optimization, not with respect to sort of an artificially ineffective baseline, but just as a series of optimizations, assuming some realistic constraints on the optimization. So we start by assuming that the layout has to be gridded. In like Vineyard, we assume a 1 nautical mile interturbine spacing, and then using some suggestions from the advisory board, we look at either the grid has to be rigidly north-south, can it be rotated, can there be shifting in between the rows, and things like that. And then we perform this optimization purely with respect to AAP, not with respect to costs, which is again a recommendation from the advisory board. And that leads to this. So we get for each of our constraints, so if you fix to north-south, you can put 42 turbines at most in this Vineyard domain using the turbines and everything that we set up. And as you allow some more freedom to the optimization, the number of turbines you can fit in increases. And then we find with an AEP-focused optimization, this really starts to develop into a packing problem. The optimizer first tries to fit turbines into the boundary, and secondly tries to minimize wake losses, which was not what we expected going in, but given the way the problem was set up, this does make a lot of sense. Also, as Nikolai talked about yesterday, there's some pretty fast wind speeds at these locations, meaning that wake loss, wind speeds that generate wake losses account for something like half the energy production. With the turbines we selected, a lot of the wind speeds are too fast to produce significant wake losses. And so the impetus for selecting for packed dense arrays goes up. And so as you sort of traverse these, we would get these results that the optimizer was continually increasing the AEP, but not decreasing the wake losses. It was packing. So that's okay. I think that's how we define the problem. That's the result we get. And this was sort of consistently observed even for the sites that were directional. So maybe going in, we thought, well, the directional sites, you'll just design them in a way that don't have wake losses. The wake controller will have nothing to do. But I think in our case, and maybe in a lot of cases, some combination of regulations, compromises with shipping and fishermen, the desire to fit in as many turbines into the expensive lease area you bought, mean there's going to be wake losses, mean that there's going to be something for wake steering to do, and you'll have this degree of freedom then to cut into wakes. So that brought us to the next phase where we started using the wake steering optimizations. Something like 6 minutes, I think. Okay, yeah, great. Okay, so we start running the wake steering optimizations across these sites, so Hawaii, Vineyard, Humboldt, for all different setups of the layout optimizations for different assumptions over turbulence and things, and we start to see a pretty strong relationship. So dependent on the amount of baseline wake losses, it becomes fairly predictable the amount of AEP uplift you expect to get from wake steering. So 5% wake losses in the central case, which was sort of a medium case in between some different extremes, might yield 1.35% AEP uplift, where 10% wake losses goes up to 3.1. And this is optimal, so not including like practical knockdown of you can't yaw instantaneously. So maybe 2/3 of that achieved in practice. But I think these are encouraging numbers from our perspective. And with some of the wake loss numbers being said yesterday's meetings, I thought very promising. So we'll see. When we went over to cost modeling, things get a little bit more complicated. So in the cost modeling brackets, we have to, for each of the layouts, we have to produce an assumed cable layout. And then using some of the NREL tools, we can work through to levelize cost of energy. And here you see some slightly shifted preferences. So, like I said, if you go for AEP only, it goes for the densest case up here is the best. But in terms of minimizing LCOE, there's a slight preference for this less dense case. But in general, the AEP uplift from control passes directly through the LCOE formula, and you get almost a 1-to-1. So any improvement to AEP shows up as an LCOE. And then the final thing, which wasn't part of our original work, but we've been interested in at NREL, so we wanted to try to squeeze it in here at the back, is looking at revenue impacts. So if you, and we have a paper coming out on this for onshore soon, so we wanted to take a look for offshore. If you assume that there's no relationship between wind speed and electricity prices, and you say, then you do some sort of very simplistic revenue calculation, then clearly, so that would be this black line here on the wind speed to dollars per megawatt hour curve. Then a farm that yields 1.54% AEP will yield the same amount of revenue increase. But some recent papers suggest that as wind energy concentrates, there is an increasing correlation, negative correlation between higher wind speeds and electricity market prices. So some papers looking at West Denmark and things like that. And so we started to say, another reason to consider wake steering technologies is that they act at low wind speeds. So this figure is showing for the vineyard case, these are the wind speeds which gave us all of our increases in energy yield, and they will correlate, generally speaking, to the higher electricity prices, where in Denmark, as you got over 20 meters per second, you're starting to see €0 prices and things like that. So that can cause your impact on revenue to be outsized because it's a low wind technology, and if that correlation comes into existence with the buildup of U.S. offshore wind, it gives you a little bit more incentive. So all in all, we thought a very positive story here at the end for the value of wake steering for U.S. offshore wind farms to be considered. And big thank you to NOWRDC and all of our partners.
Great. Thank you, Paul. And turning over to you, Eric.
As Julian mentioned, I am not Eric Smith. I'm Eric Sells, the generic brand of Eric, I guess. So I'm subbing in, but I'll give our presentation for Keystone Tower Systems today. Keystone Tower Systems is a tower manufacturer. We actually are really more of a machine design company who just happens to manufacture towers. And we're really one of these innovative technology companies. And I think that's highlighted in the project that NOWRDC is helping sponsor. So here on the left, you can actually see our spiral mill with about a half-completed tower section on it. And here on the right photo is actually our first commercial megawatt scale tower that we installed about a month ago. I do have a video. This is not the PDF, so also a video that's not going to work. So I'll just describe our manufacturing technology a little bit. So again, here on the left, basically we feed in sheets of steel. We weld them end on end to create a long ribbon. We then roll that ribbon through our spiral mill. It simultaneously bends that into a round shape while also welding it so that it's a continuously fed automated manufacturing process that you're essentially just feeding in a ribbon of steel in one side and producing a tower section on the other. So the commercialization of this technology is kind of demonstrated here. In the last couple of years, we've been building our first manufacturing facility in the panhandle of Texas. So like I said, we just installed our first megawatt scale tower. That's been a long time coming. Just getting a factory up and running takes some time. We're going through our ramping phase currently, so we'll be able to produce about 1 gigawatt worth of onshore towers out of that factory when it's fully up and running. Simultaneously, we're developing an in-field or on-site fabrication technology. So the benefit there is we're basically scaling up the diameters of these towers so that you can have a much more efficient structure that normally you cannot ship across highways due to bridges and other logistical constraints. So you would move a factory into a large field that might be developing several gigawatts worth of towers, turbines, and just park your factory there for a few years, fabricate the entire field, demobilize, and move to the next one. And because the structures are so much more efficient, you can pull a bunch of steel out of them, and all of those cost savings actually more than pay for the mobilization, demobilization of the factory. So that's how we get larger diameters. And the current project that we're working on, funded by NOWRDC, is to also upsize the wall thickness. So towers are diameters are relatively easy to upsize, but increasing wall thicknesses require higher bending forces, much more weld passes, and it's just, that's a trickier problem to solve. So this again is kind of demonstrating how our technology would then specifically apply to the offshore space. So currently our in-field factory mill would be able to manufacture offshore scale tops and mid tower sections. So in the range of 7 to 8 meter diameters with around under 35 millimeter wall thickness. That needs to scale up in order to do bottom sections. We think our current technology is capable of doing that with a few modifications to the design, but maybe not so efficiently. So what we would like to do with this technology, or with this project, is to do that much more efficiently. And one of the ways we're going to do that, attempt to at least, is through a multi-wrap system. I'll talk to in more detail in the following slides. But if this is allowing us to get larger diameters and then arbitrary wall thicknesses that scale more efficiently, we can be manufacturing monopile foundations, floating substructures, much heavier tower sections of the turbines of the next generation. And this is, I guess, why we're in the fixed structures talk, because monopile foundations might be part of that discussion. So traditionally, the industry, as turbines get larger, wall thicknesses have to increase in order to hold those loads. Then wall thickness of the structure has to increase. This would be our traditional single wrap technology. This is to demonstrate that the bending forces actually increase across the wall thickness, and you must then have to fill all of the welded connections with many weld passes. There's also an important supply chain piece to this. A number of steel suppliers able to manufacture, say, 5 or 6 inch thick plate for these monopiles are very scarce. To my knowledge, there's one in the United States, and I think anybody trying to source from them knows exactly where they are. So our technology, this multi-rep option, would essentially, you'd manufacture a tower or a monopile, and then with 1 inch approximately coil material, you'd then have to subsequently feed that through the spiral mill any number of times in order to achieve the wall thickness that you're seeking. So the benefits would be obviously less bending force. I think the best analogy I've heard here is kind of like bending a phone book. it's very easy because all of the pages slide past each other. So each one of those pages is very easy to bend. But when you go to pull on it, it acts like a block of wood. All of the fibers are resisting you whenever you're pulling just in tension. So that's sort of the analogy. I think that we're able to use less bending force when constructing the tower, but whenever it is a completed structure, they all act in unison and are efficient. So then also the number of weld passes are less as you're developing the structure. And as I mentioned, we actually would be in a totally different supply chain using hot rolled coil. The prices are actually, sorry, I am playing music in my pocket. Sorry about that. Okay. So yeah, we're using hot rolled coil, and the prices currently are at around their historical norms, while the plate market is not, and they're about half the price due to this abnormality. But even on the long run trends, it tends to be a good couple $100 less per short ton. So some of the questions then are this is kind of a novel concept as far as we've used composite materials, obviously, but rarely is that applied to something like this scale of thickness of steel. And so some of the questions are buckling of the completed structure and fatigue, which I'll get into later. Our partners, Johns Hopkins and Northeastern University, Andy, thanks, are helping us with the buckling piece of this. And so, I want to describe kind of what we're trying to solve here. If this is a tower section, and you can imagine taking a slice out of that tower section, then applying a compressive load on that single slice of your wall, that will have a tendency to, under a certain critical buckling load, actually bow out and buckle. Once that begins to happen, if those walls of your structure are acting independently, then the buckling load is as if each one of those walls buckles completely by itself, and you have a relatively low load at which that occurs. And that's because they can just slide past each other, bow away from each other. They're just totally acting independently. So in order to prevent that and make them behave as if they're one solid wall, you need to develop shear between them so they can't slide and they actually rotate together. And so what I'm showing here on the lower left is a curve that shows the load factor against that shear modulus, so some resistance between those layers. There's two plateaus. On the low end, this would be whenever they're totally unbonded, you see a low load at which they buckle. At the top plateau, it's as if this is one completely monolithic structure acting as one heavy wall structure. And somewhere in between, we need methods of connecting the walls, whether that's rivets, adhesives, some sort of connecting mechanism. And we're in the midst of defining what those materials might be and how much exactly shear resistance we need between those layers. And I guess this is a good time to mention that we're we're in the end of phase 1 of our 3-phase project. So we've begun work. These are actual outputs from Johns Hopkins on the left here, but without really conclusive numbers or anything like that as far as results. And then we're also going to manufacture a test specimen, and they'll be tested here by Northeastern, and those will feed back into the models to validate them. The next piece of this is fatigue. And so, similar story here. There's not a bunch of just fundamental, or there is a need for just basic fundamental research on this. There isn't an existing weld detail that mimics the type of structure we're creating. On the left, I'm kind of demonstrating an existing fatigue detail category that just really is the closest option to compare it to, but does not mimic our structure. And what I'm trying to show here is, as you pull on this structure, this would be from like a ship deck or ship rib. As you pull tension on this, it not only pulls tension on the weld, but also transmits some force through the backing plate, which would then create a bending moment into at that weld location, which actually creates additional tensile forces on the surface and creates additional damage for each fatigue cycle, and it will fatigue more rapidly. Whereas our structure, we are actually welding it all together and pulling it along its axis, and we're not getting that out of plane bending. So a little extra detail on the right here. This would be like our looking at the sliced cross section of a tower. This inner layer would be our traditional tower manufacturing technique, where you actually have a double-sided butt weld. Subsequently feeding it through our spiral mill, you would put a butt weld in and weld that into the existing mandrel tower. And so it actually, this weld will penetrate into the existing tower. Each step you have to grind off the weld caps so that the subsequent layers can lay flat. And you can, like I said, do this any arbitrary number of times in order to build up the wall thickness of your structure. So we're going to, we have done the manufacturing of this in plate form in order to develop dog bones so that we can perform some fatigue testing. And so that is depicted here on the right. And the next slide here are some of the fabrication photos that we've actually performed. So we developed the weld procedure just using sample plates here. And this is really promising that I've kind of overlaid some drawings on this. This is actually two separate pieces of steel, and I just drew that dashed line because they're pulled in together so well that you really can't even see it. Then we etched this surface, and you can see that we actually performed two separate weld passes. You can see the first weld here outlined in this dashed line, so it's actually penetrating into the existing bottom plate. And then we performed a second weld in order to get that nice, to fill the void and to get that nice rounded cap. Once we validated our weld procedure, we sliced those plates up and performed a side bend test. And you can see here, this is actually bent 180 degrees across this weld, and it's performing really ductily and not continuing to crack through that weld. And then here on the lower right it's a 3-layer panel, as I was showing in the previous slide, and we just finished these this last week, and we're shipping those to the test lab currently, today actually. And then I just wanted to mention some other aspects that are sort of beneficial with working with Keystone, and that this project is allowing us to explore as well. So we're looking at realistic port locations all across the U.S., including the Gulf and the West Coast now. I mean, they're having their first lease auction out in California today. So we're looking not just in the Northeast. But one of the benefits of Keystone Tower Systems is our rapid throughput through our automated system, so that we can actually have much smaller footprint facilities. And it's possible to co-locate actually on the marshalling yards or much closer to them to knock down those transit times and costs. And there's a local content piece of that, and diversity, inclusion, all of that stuff as well. Actually bringing manufacturing where it's needed most, or to existing or recently abandoned areas, and revitalizing areas a little more surgically, perhaps. And it's also worth noting that we are using our existing domestic steel supply, and that it is of low carbon content, which is also important if we're the reason for our entire industry's existence is trying to minimize carbon. And so it's worth noting that we're using low carbon steel. And it's in-house design. So some of the other speakers today have talked about either very rigid gravity-based structures, and those are going to have very different resonant frequencies than a steel structure. Paul was talking about controls, and so we could even just design our towers to have appropriate resonant frequencies. The water levels, water depths might change for a given field, which might impose a penalty to steel on your substructures, and we can help compensate for that in our design. So bringing that in-house means we collaborate directly with the OEM and produce more efficient structure, as well as avoiding other logistical concerns like air drafts and just overall project logistics. And with that, I'll call it good. Thanks.
Great. Thank you, Eric. Back slides here. Moving on to the final presentation for this session. So thanks. Welcome the other Eric up.
The other Eric. Well, thanks, Julian. Well, first of all, thanks for giving us the floor here, and to NOWRDC for their kind contribution to develop our TSPC foundation a bit further. I will talk about a suction pile foundation. Well, I was happy that Charles already explained quite well how suction piles work, so that's a given. This is an alternative to the suction pile foundation, and I hope to guide you a bit through this sort of this alternative foundation, because we do see certain particular advantages for the US application. Well, briefly, how is the presentation built up? Briefly, we'll talk about the team, a bit deeper on the tri-suction pile caisson foundation. We already performed a market assessment, and a last slide on the timeline. But we just started this this work, so there's not many conclusions yet. I did hear a lot of interesting information from the previous presenter, so I think I already learned a lot that we can implement in a coming phase. But I hope we get another opportunity in about a year's time to present the results. Well, briefly on the project team. I'm from DEME. DEME is, it sounds a bit boasty, but they're, when it comes to offshore wind turbine and foundation installation, more or less the biggest in the world, the biggest experience. Also very active now in the US in a number of wind farms. More than 5,000 people. They operate high-spec jackups and heavy lift vessels. SPT Offshore, that's the company I work for, is a subsidiary. It stands for Suction Pile Technology. And we're active in this field for more than 25 years. Initially in oil and gas, but luckily we moved more towards the renewable sector. It's quite interesting when you see that typically in oil and gas we did like 1 or 2 jackets per year. And in the wind sector, the same happened over the last 10 years, but 2019, we installed 11 jackets in Aberdeen Wind Farm. 1 year later, it grew to over 70 jackets in China, while China is now picking up further on the suction bucket jackets. Seagreen is more than 100 jackets. They're being installed as we speak. So you see a really quick ramp up from almost nothing to, yeah, it's almost like a conventional foundation already. But the TSPC is an alternative to the suction bucket jacket, and I'll explain it in a moment. Briefly on the team, on the left side you see Jan Klaassen and Sydney Flory. They could unfortunately not join here, but when you meet the demo guys, you will quickly meet these. And yeah, unfortunately I see that Constance is here in the room as well as Zach. So the picture is a bit weird, but they can also guide you, can inform you better about Dema's capabilities. And they were responsible for the more business part of the development. Well, what is this TSPC about? You all know jackets, and suction pile jackets is basically a bit what you see here. So the bottom part, the brownish part, are the suction buckets. That's the part that is being penetrated into the soil, and that gives the foundation of the structure into the seabed. And normally on top of these three suction piles, you would see a jacket. That's the conventional foundation. And suction technology offers a tremendous number of advantages, which I will quickly show. But what we realized is that jackets, although from a structural perspective, they're really brilliant structures, because all the loads are being transferred nicely into tension and compression. So from a structure point of view, that's the best you can have. But fabrication-wise, it's a bit more of a complex structure. You can imagine that the connection between the main legs and braces is quite a complex 3D-shaped detail. It's quite expensive. So that's the reason why the idea within SPT came up a number of years ago to sort of combine the typical monopile with a suction bucket foundation. So it's a bit of a hybrid. And the whole idea behind it is that, yeah, monopiles can be fabricated a lot cheaper. They are being fabricated fully automated. It's when you ever have the chance to see it at SIF or EEW or Steelwind, it's a beautiful process. There's hardly any welder. They're just sitting behind their screens to watch the process, but everything is done fully automated. And as a consequence, and now I have to admit that the price levels that I'm now mentioning are the beginning of this year. A lot has happened, obviously, but the beginning of this year, typical price levels of a monopile foundation in Europe were around 1.8 to 2.0 euro. Well, so let's say that's about US dollar, just to give a feel. If you compare that with a jacket, that's typically around 5 euro per kilogram. So although the jacket is, from a structure point of view, a smarter structure, and it's also more lightweight compared to a monopile, the fabrication costs are so much higher that it's still interesting, commercially more viable to go for the monopile. Well, obviously we go to deeper waters, the turbine sizes grow, so monopiles come a bit to their limits. One aspect especially is noise. The larger turbines, the XL or XXL or XXXL monopiles become so large that even if you pile drive those with relatively small hammers, simply the size of the monopile, it works like a loudspeaker. Since the area is so huge, the noise generated is also huge. And this year there were some projects where they had to use multiple noise mitigation systems in parallel, and they were still not able to stay below the criteria. And that can be quite painful, because basically the project can be halted. Well, the interesting part about suction pile technology is noiseless. So when you install a suction pile, the most noise is generated by the vessel propulsion system and not by the pile driving. So yesterday I heard a lecture about I think it's the right whales, obviously a big concern over noise, And this is a solution. Pile driving will see piling bands overnight, certain seasons because of waterborne and airborne noise. And with suction pile technology, that's not the case. There's no issue there. Another interesting aspect of suction piles compared to pile driving is with pile driving, the structure is being subjected to really high accelerations in the order of, I believe, thousands of G. So it's whatever you weld to the structure, it's simply being vibrated off. It just breaks off. With suction pile foundations, the process is really elegant and smooth. So there's the burst acceleration you will see when the foundation is sitting on a barge and being transported to field. So that allows you to pre-install all the secondary work already in the yard. And we all know that doing work in the yard costs about 1/10 of what it costs to do it offshore. So there's a big benefit there. But it also allows us, for example, to pre-install a scour protection system, not the rock-based system that most of you people know, but we have a system which can be deployed from a suction pile. But you can simply pre-install it, carry it to the field, and then deploy it. Another element I would like to mention is nature-inclusive design. We are working on a sort of similar development in the Netherlands where we include reefs and special structures to attract oyster. In the northern part of the Netherlands, there used to be really large flat oyster beds, reefs, and they are completely vanished due to fishing activities. And our intent is to prepare a design to bring back this oyster culture by pre-installing these nature-inclusive design elements on the structure. And again, since suction pile is the suction process is really elegant, you can pre-install all this matter on the foundation. Let me see. On recycling, it's good to mention that with monopiles, we drive them in the sea, but we still don't have a real plan to get them out. Obviously, there's a lot of developments going on at the moment to see if it's possible to, commercially viably to get them out of the seabed. Not easy. The interesting part of suction piles is that you can pump them out. So you can retrieve the complete structure, and once removed from the seabed, there's basically no trace left on the seabed. It also says suitable for US soil conditions. It's maybe a bit bold because it's not suitable for every soil condition. In case there are boulders or coarse gravel, it's more difficult to, I would say impossible to install suction pile. But in case of clays or sands, even stiff clays, hard sands, combinations of those, it is possible to install, but you do need to look at the installability on a case-to-case basis. Something to mention here, because I will come back to that in a moment, is the double slip joint. So in the center you see this monopile. The bottom part is obviously the base. And these can be split by a so-called slip joint or a double slip joint. It's basically the same principle, and that's the reason why I brought the coffee cups. It's nothing more than that there's one coffee cup, a bit larger, sitting on the base, and the central column is outfitted with the same. And once you join them, they are completely tight. This concept was tested last November in the North Sea, the single slip joint within a large consortium. But we team up with an engineering company called KCI, and they have we think a smarter concept where they've divided into two concentric rings. So it's more lightweight and it's more accurate, and it's called a double slip joint, but it's principally the same. And no grouting needed. You can plug it onto each other, and then it is capable of transferring all the loading. Good. Well, it's a bit on the suction process, but Charles already explained it quite well. But I think the message I want to convey is that suction pile driving is a very, it's noiseless, but also very elegant and very slow and accurate process. In 2019, I was on board the vessel where we had the ROV visuals on the bridge, and you could actually see how the suction pile was slowly being driven into the seabed. And then once you stop pumping because you want to correct on the two other suction piles, it immediately stops, and you can very nicely play. You can also pump out again if you like. So it allows you to very accurately control inclination. So therefore, let's say putting on a transition piece to correct the inclination of the structure is not needed because you can do it in the structure itself. Well, one part that we have finished was a bit of discussion is on the basis of design. The intent is to prepare a design for specifically for the US market. And we chose for the 40 meter water depth. And the reason why we chose for the 40 meter is that the feedback we got from the monopile manufacturers is that they see that the monopile will come a bit to its limits at 40 meters because of the size, because of the noise mitigation issues, also because of handling issues. The piles become really heavy and tall, and then handling is also starting to become a problem. So the 40 meter is like an interesting area where we think that alternative foundations will come into play. Obviously, we look at 15 megawatt turbine. That's the current state. The advisory board already requested to also look at bigger turbines, so we will also make a design for that. Logical question, 90 megawatt, 20 megawatt will come into play by 2027 around. So it's a logical question which we will take on. We focused on the US coast area. An interesting part of that is that initially we just started off, let's say, on a European basis. And then one of the advisory board members flagged that, you need to do a business check because you have the hurricanes flying by. And you have to adhere to the ABS 500-year business check. And it was a bit of a shock because we made a very preliminary design based on sort of parametric formulations we've learned from previous designs. And we did this quickly did this check, and it was quite shocking. It has a big effect on the design. We think we can cope, but it's certainly something we need to take into account for the rest of the, let's say, during the detailed design phase. There's a big impact. For the soil profiles, we initially thought that just looking at only sandy profiles would be enough. But after a bit of a survey of on the soil data of various wind turbine areas in this area, we found out that there's quite a big variation in soils at the U.S. East Coast. So we decided to also include a sort of a multi-layer profile, sand, clay, sand, which is a bit of a nasty one for installation. But thereby we cover, roughly about 40 to maybe half of the sites in this area. Well, the first design, the initial design, we come to weight for the base or between 1,700–1,800 tons. So it is quite a heavy base, completely agreed. But for the column, so 500 to 600 tons, we hope to be able to scrape weight off. Showing this, you now see a completely steel design, but we quite quickly realized after doing a market survey is that in the US the concrete industry is quite strong, and that was a reason to also include a concrete design. So the connector between the suction piles and the central column, we now intend to also design in concrete. And I'm a steel guy, and I do not have any clue about concrete. I'm really interested to learn what will come out of that. Well, you just on the previous picture that it had base and the column can be splitted, and the whole idea behind it is that the column, the base can be towed out, free floating on the air pockets inside the suction pile, and then in the field it's lowered with a somewhat smaller heavy lift vessel, so not the big units that we will see in the next years, but let's say a past generation heavy lift vessel. It can be lowered to the seabed in a controlled manner. Basically, it can be tuned to almost zero buoyance, but, well, obviously you would always keep a bit of load in the crane. And then next, the central column comes in, but because the central column is quite lightweight, the capacity requirements are also not that big. Market assessment has been done, looking at the, we did a SWOT analysis for this particular kind of foundation, where obviously the strengths are very much into the noise, the fact that there's no noise generation. So we do not see any schedule issues there. We will not be kicked off the work. A weakness maybe is that the suction pile foundation is not apt for every soil, so we need to look on a case-to-case basis whether that will fly. Opportunities are obviously into the elements like the concrete industry. If we're able to make an interesting match there, it's going to be a very interesting opportunity for us to get the TSPC to work and for the US industry to generate work. From the initial market assessment, I'm not going to tell that much, but we heard quite a lot already from the other guys. And to be honest, I found your presentation also interesting, Eric, because I realized that we now need to talk to you about the monopile. But a lot of stuff that we noticed is already said today. And also yesterday, we heard a presentation. I forgot the name, Doc was his name. And they're also working on a report which will be issued at the beginning of next year about the US markets. So there's a lot of work done there. But we see a lot of constraints, and these constraints will be taken into the design of the TSPC. Just one example, we want to float out the structure. That means that we need at a draft of about 12 meters. So you would need a channel depth of around 14 to 50 meters. Well, that's quite a problem we noticed in the US. So we need to adapt our load out and transport and installation methodology to be able to cater for that. Last one on the timeline. We've finished the initial market assessment. It clearly says initial because we noticed that there's a lot happening at the moment, so we intend to issue an update on this one. The base of design has been agreed upon. That's done. So we're now in the phase where the basic design is started. 2 tracks, a steel one and a concrete one. And we hope to have that finished by February, maybe a bit later. And that is the starting point. And that's I think the main gist of this study is that we can then start with the cost analysis. Obviously, a lot has happened in the industry. Steel prices went up last year, but have gone down again. Fuel prices remain high. Inflation has also hit the cost of employees. So personnel cost has increased suddenly. So the whole cost environment has changed. But we will use, as soon as we finish the design, we can do our cost exercise. And compare to conventional suction bucket foundation to see, for which, whether it's going to be commercially viable, but also find out for which niches this foundation will become interesting. And then by the end, by mid of this year, we will finalize all the reporting. And any questions? Interested to receive those. Thank you very much.
Okay, great. Let's see, move on to this slide again. So yeah, we've received a number of questions in the Slido app. Part of the functionality of the Slido app is that you can upvote questions that you're also interested in. So those come to the top of my list, and that's what I'm looking at. So if you see things there that you want asked, do that. And then, we have about 12 minutes for this, finishing at noon. So I'm gonna get right into it, but probably or definitely will not get through everything. So please feel free to follow up with those who your questions weren't asked afterward. So I think I'll start with this question for Keystone. Was what percentage of employees to operate the mobile tower construction facility would/could be hired locally in these places where you set up that facility?
Yeah, we would need to set up the facility with our expertise, but after that initial setup, it would be primarily local jobs. It's primarily welding and just heavy fabrication work.
So somewhat related to the trades that would be available in each location,
Yeah.
dependent on location.
Yeah.
But yeah.
Yeah, and we're expecting organized labor and all of the things that I think are going to be part of the Northeast workforce.
Yeah, absolutely. My phone keeps locking me out here, sorry. All right, so I'll move on to one for you. Charles, upvoted by a couple people. They're questioning how long the wait time would be for reconsolidation of soil, I think, with the Vibratory installed.
Well, in sands, it's not too long. Well, one, it's a topic of future research. We didn't look at it in this project, but there, at the recent ISMOD project conference in August, there were several papers on that. So I don't have them off the top of my head, but I'd be glad to.
Deferring to public resources, and you can email Charles afterwards.
Yes.
Okay. One for you, Paul. How sensitive is the benefit of wake steering to the choice of wake model used?
Yeah, fairly sensitive. So the wake models predict different amounts of overall wake losses. So that's a big determinant. And then you can make variations on the effectiveness of wake steering. So in our project, we saw AEP gains from below 1% up to maybe 4% across the cases considered, depending on if you went for like 100% of the strongest or weakest assumptions, then in between.
Yeah, so it's a lot of variability within that. Still trying to hone in on exactly where is the most accurate then.
Yeah, and I presented our central assumptions, so
Right.
the ones that we feel best about.
Great, thank you. Okay. As things are upvoted, it shuffles my list around, so bear with me as I get back on track here. Okay, question for you, Jose, is the floating system wet tow out option robust enough to allow for mooring of the foundation while you might need to wait for appropriate conditions, weather window, and or support crew to arrive on site? If you can install right away, can you moor it and wait for
Yes, I understood. Yeah, yes, it is possible. Of course, when you tow out, you look for your overall window, but if you need to wait, you can wait with your tugs. In any case, maybe that wet tow was also directed to the wet tow installation with the suction buckets. Because we are planning to use buoys, and so that's in our case we have our team structure is quite stiff structure, so we can tow directly pulling from that, and they can remain in position. But yes, the installation window, since we leave the harbor, it's a whole window, and our forecast should make sure that we remain with below the weather restrictions for the whole installation window.
Yeah, sure. So maybe I can sort of follow on that question from my own curiosity and past calculations on similar structures. I think part of the question is sort of stability, the stability question. If the weather escalates beyond your window, if the weather window isn't met and conditions get beyond what is expected for installation, is that TIM platform providing enough stability up to higher potential waves and winds?
Yes, it does. It's defined by the code, so you have the alpha factor, so you always look for a forecast that will have a certain margin with respect to your design. But of course, this alpha factors also depend on your forecast and how often are you checking it. Because yes, at the end of the day, it's a weather restrictive operation, so you need to make sure you don't go beyond those limits. There are margins, but yes, at some point we are designing for 2.5 significant wave heights, and I think the alpha factor means we don't go out unless the prediction is below 2. But if it went to 3, then you may need to take you need to, as I say, any other weather restricted operation, you need to keep a look on your forecast. Indeed. Yeah.
Okay,
Mhm.
great. That's helpful. But there was a question on your wet tow, specifically, Charles, here. So how is the floating stability ensured when the floaters, the buoys you presented as a concept, go underwater during the installation when the bucket and water plane inertia is lost?
Yeah, that's asking all the questions outside my ear, but that was Professor Kim. He had 2 reports on that where he did discuss that. So 2 of our deliverable reports, he demonstrated the stability that you're talking about. So, but I can't speak detailed on that because that was his.
Yeah, no, good.
details.
And then that presumably, or at least the conclusions of that will be in the final NOWRDC report, which would be
Yeah.
presented
Mhm.
publicly and
Yeah.
available on our website when
Yeah.
the project has finished. So. Great. Question for Keystone. So this is a specific question regarding the weld connection on the flange. Are you looking at that as part of this project, and how is that potentially complicated by the spiral wrap welding?
Yeah, it's actually outside the scope, but we are doing that development in-house anyway. We haven't done it yet. I'm actually pretty optimistic based on the fatigue panels that we put together. We were initially afraid that that gap in the plates would cause kind of loss of the weld bead into the seam, and we just really didn't see that. So it really did behave almost as if one monolithic piece of steel. So to be determined, but I'm optimistic.
And then another one for you, which I'm not looking at exactly, but it was regarding the grinding of the welds between layers, which you mentioned. But I think the question is that a totally manual process? Is it built into your machinery? How are you handling that?
Yeah, that would be a new process, but the concept would be to automate it. A lot of the factory is automated. As that tower would roll out through our out of our mill and to feed out, it's rolling through that process. So you could just have grinders even graded, aggressive to less aggressive as it passes through that system.
Yeah, cool. Charles, one question getting bumped to the top for you is, how does the installation of vibratory or suction mono buckets ensure verticality of the pile when geotechnical conditions may or are not homogeneous?
Yeah. One advantage of vibratory I didn't talk about. There is a hook line that maintains tension, so that could help a little bit. Having said that, our other system, if you have the tripod, you could correct as you go. But for the bucket itself, though, I think with the hook line maintaining tension, be a little bit easier to maintain verticality than the suction for the bucket for a single bucket.
Yeah. Okay, great. So I think I touched on a lot of the ones that were getting upvoted. I'm going to go to what I think is a pretty general question. It might not exactly be in your wheelhouse to answer, Paul, but when it gets down to you, please chime in if you want to. Something I was curious as to what all of your thoughts are, and it was mentioned by Jose specifically that your fixed bottom technology, you're looking at designs up to feasible for 65-meter depth. But the question is that 60-meter water depth has basically been the cutoff water depth used for understanding and in practice where we go and transition as an industry from fixed bottom to floating techniques. And so my question is, given the improvements in fixed technologies that your products are part of, and continued learnings track record of deeper fixed installations, do you each foresee fixed structures being selected for deployment in even deeper depths? And I think a number of you can answer on this, so if we can start with you, Jose, and move down as you wish.
Yeah, that's a big question, the frontier between bottom fixed and floating, where to place it. I do think that bottom fixed solutions could go to the 60, 70 meter water depth range. And we have worked on that, and even though floaters are also getting more and more competitive, at the end of the day, all the mooring lines, and there's a big cost in there. So if you can go for bottom fixed, you typically can expect some savings. I don't know if there's a limit. I know that's what we have worked on, and it's still operative, and it can be built and can be installed. So we kind of place that frontier in that area, but it's not like something fixed or that we have not a specific study for that.
Yeah. Now, Charles, you want to comment?
Yeah, I think right now 60 meters seems to be the rule of thumb. I think the problem is that the floating is less mature, so it's hard to draw a boundary when we don't really know the exact economics of the floating. So I think like the last answer was until they're two both matured technologies, it's kind of not real easy to say what that boundary is going to be.
Yeah. Yeah. And Eric, so do you think your technology becomes applicable?
Well, in Europe, we've already seen tenders passing by for suction bucket jackets deeper than 60 meters. But if it would fly in the US, I wonder, especially because it is 500-year robustness check, the wave loading on the structure is really tremendous. And the deeper you go, the more of a problem it will become. So
Yeah.
it may fly in Europe, maybe less in the US.
Oh, that's a good perspective and a good detail,
I'll comment. So we are currently manufacturing towers, not substructures. But as I mentioned, we are more of a machine design and innovation company. So I'll take the agnostic approach and say that we would just as gladly manufacture floating substructures as monopiles. So I'm optimistic to see where the floating structures, all those innovations, kind of drive down costs and where that equilibrium reaches.
Good. And not to take your voice away, Paul, are you curious in chiming in, or just happy to be here? Great. All right. No, so thank you. Join me, please, and thank you to that panelist.
Oh, sorry, if I may, I have a question actually to Paul. I can imagine if you have floaters, you could do like dynamic mooring to get a better wake, in order to avoid the wake problem. Would that be feasible, do you think?
There have been research projects to look at it. There's some, probably complicated. It is feasible, but you have to move a bit. Would be my answer. So you can't move just a little bit. So your plan has to be to move at least half a rotor diameter.
Okay.
So if that's feasible, then things become feasible.
Yeah. So California 1,000 meter water depth, that sounds feasible then.
Yeah. Okay. Cool. No, that was interesting. Thank you, Eric. Yeah, but thank you all for your time today, and thank you to the panelists.
Right.